Okay, so this series of lecture videos starts off uh, with an introduction to confidence intervals. So recall when we want to try to estimate a population parameter. Uh, so, for example, uh, population mean or population standard deviation or population proportion. Then what we do is we compute a statistic from a sample. We call it a statistic. Statistic is basically a rule that approximates a population parameter. And in fact, we call uh, an estimate of the population parameter a point estimator for theta. So theta we reserve as the population parameter, and the estimator we call theta bar. So numerical value given for the point estimator is called a point estimate theta. So, for example, if we want to estimate the population mean, the true population mean, for example, the lifetime of bad rate, then we compute as a statistic a point estimator x bar, which is the sample mean. If we want to estimate the population parameter with the standard deviation of population, we compute the sample standard deviation. If we want to estimate the population variance, sigma squared, then we compute the sample standard deviation. If we want to compute the population proportion p, we estimate it by computing the sample proportion. So, for example, if we investment manager looking at HSBC wants to estimate how well his 50 portfolios are doing. So instead of looking at all 50, he just looks at 10 of his portfolios. And in thousands per year, they're earning 95, 96, 89, blah, blah, blah. It's 50, 79,000 Hong Kong dollars per year. So how much? What's the point estimator for the true mean of how well his portfolios are doing? Well, we just find out the sample mean. So 95 to 67 all the way up to 50 plus 79 divided by 10. So in fact, the estimate of the how well his portfolio is doing just by taking the sample mean. So on average, he's making 74.9 thousand Hong Kong dollars per year, and to compute the sample standard deviation, we use that formula, right? Summation xi squared minus x bar squared over n minus 1. So this is 95 squared is all the way to 79 squared minus mu squared. So 74.9 divided by squared divided by 10 minus 1, which would be just $247,65,000. So we say that estimator is an unbiased estimator. So theta bar is an unbiased estimator for population parameter theta if the expectation of the estimator is equal to the population parameter. The expected value of the estimator is equal to the population parameter. So, for example, we know that the expectation of the sample mean distribution is in fact, so that's just going to be the mean of the population. So the sample mean, is an unbiased estimate for the population. Also, the sample proportion is an unbiased estimate. for the true population proportion, P, since the expectation of the sample proportion, right, is just equal to the population proportion. This is from section 12.2. This is from section 12.1. And also, the expectation, so the sample variance is an unbiased estimator for the population variance. Since the expectation of the sample variance is in fact just true population variance. This is from section 12.3. An estimator is efficient if it's more efficient than estimator theta 2 if variance of theta 1 estimator is less than theta 2. When we say that an estimator is consistent, if the sample size increases, then the variance of that estimator goes to 0. So, for example, in fact, the sample mean is a consistent estimator since we know that the variance of x bar is just the sample mean distribution is sigma square over n. Then it goes to 0 as n goes to infinity. So now we define what we mean by 100% times 1 minus alpha confidence. So this is how confident we are in estimation of the true population parameter. So we say that we have 100 times 1 minus alpha percent confidence in the estimation of parameter theta is in the following interval L1 to L2 if the probability that theta lies in between L1 and L2 is 1 minus alpha. Okay. So picture-wise, this is L1, this is L2, and here's the population, here's the probability distribution. Then we have, then alpha, the true population parameter must lie in the shaded region with probability 1 minus alpha. So some common values of alpha we'll take a look at are alpha to 0.1 for 90% confidence interval, alpha to 0.5 for 95% confidence intervals, and alpha to 0.01 for 99% confidence intervals. And in the next video, we'll learn how to compute some confidence intervals.